All right, we'll wait one more minute. All right, well, let's get started. So welcome to the penultimate Western Hemisphere Colloquium on Geometry and Physics. It's the penultimate one of this academic year. And as usual, if you have questions during the talk, just interrupt politely or use the chat, and there will be an opportunity for questions after the talk as well. So we're very pleased today to have Pavel Safronov from the University of Edinburgh, and he'll be talking to us about holomorphic Morse theory and moduli spaces of flat connections on three manifolds.
Yeah, thanks for inviting me. It's great to be able to speak here. So I want to describe some recent works and some works in progress, which are broadly related to trying to make sense of Morse homology of the complex Chern-Simons functional. So let me introduce the main ideas. So in this talk, I'll be considering some manifold Y and a closed one form. And so if you have a Riemannian manifold and a closed one form, you can consider supersymmetric quantum mechanics with target Y and potential specified by this one form alpha. If you like, you can think of alpha being d of a function, which is the potential. Now, the main example I want to consider is where you consider a higher dimensional theory, so not a one-dimensional quantum mechanics, but a four-dimensional supersymmetric theory. So if I consider four-dimensional maximal supersymmetric Yang-Mills theory, and I compactify it on an oriented three-manifold M, well, to even make sense of supersymmetric Yang-Mills theory on curved manifolds, I have to do a topological twist. So if you're familiar with topological twists, I'm going to do what are called either Waffe-Witten or Kapustin-Witten twists. They're the same on three manifolds, so you're going to get the same answer. And so what you're going to get in this case is supersymmetric quantum mechanics with target being the space of connections on the three manifold modular gauge, but connections for the complexified gauge group. So G will be complexified gauge group. For instance, it could be something like SL2C. And then the closed one form, or the potential, is given by the complex Chern-Simons functional. So more precisely, alpha is the real part of the differential of the Chern-Simons functional. Okay, and what I would like to do is to be able to make sense of the corresponding supersymmetric quantum mechanics. So how do you compute the space of states, namely, in the supersymmetric quantum mechanics, which is the same as saying or asking how do you compute the space of states of this four-dimensional n+4 supersymmetric Yang-Mills theory on the three-manifold M.
Pavel, how much supersymmetry does this quantum mechanics have?
Yeah, I'll address that.
Okay.
In general, so before I start talking about this example, you'll have n equals 2 supersymmetry. But in this case, it's actually an n equals, this n equals 2 supersymmetry is enhanced to n equals 4 supersymmetry. And that's going to be important for what I'm going to talk about.
Okay.
Okay. Right. So my talk will have roughly 2 parts. First of all, I'm going to just review various possible models of what the space of states might be in supersymmetric quantum mechanics. And then this will allow me to motivate one approach to making sense of this space of states. And I'll try to relate it to some known quantities. Okay. All right. So here's the main sort of the very first guess you can make for what the space of states is. So it goes back to the 82 paper of Witten. So again, let's say Y is a manifold and alpha is some closed one form or homology class on Y. So if you just directly analyze quantum mechanics, supersymmetric quantum mechanics, it's not too difficult to just do canonical quantization of the corresponding space. And so what you're going to get is essentially the Rham cohomology, except it's twisted by this one form. So you look at the space of differential forms on Y with the differential D plus wedging with alpha. So this is still, because alpha is closed, this is still a differential. So this twisted Rham cohomology makes sense. You can also give a topological version of this. So you can use the Rham theorem identifying the Rham cohomology and singular cohomology, or some topological version of cohomology. So you can identify this twisted Rham cohomology with just cohomology of Y with coefficients in some local system specified by alpha. Okay, so yeah, the upshot is that one way to make sense of this supersymmetric quantum mechanics is to just consider twisted cohomology. And okay, so one question I want to address is, how does this answer depend on the potential, on this choice of one form? So let me state one result. So there are many stronger versions of this result, but this is a fairly old result of Novikov from early 80s. So if you look at the simplest situation that this cohomology class is actually integral. So alpha is in H1 with Z coefficients. So you can think that you have a circle valued function on Y, and then you take its differential. So maybe I'm thinking of S1 as being R mod Z. Okay, so in this case, your alpha will define some integral cohomology class. And then what you can do is you can rescale alpha, and you can look at the behavior of these cohomology groups as you rescale alpha by some complex number, let's say. So you have this tau, some complex number, and I'm considering this twisted cohomology where I rescale alpha by this complex number. And so the claim is that these twisted cohomology groups for generic parameters, and there's a precise description of those parameters where the cohomology jumps. So for generic parameters, for generic tau, these cohomology groups are just the same. Okay. So, and this is the kind of cohomology I'll I'll be interested in, I'll be interested in this kind of generic behavior, the generic twisted cohomology of my space Y. Okay, so there are more, as I said, there are stronger statements. So I listed some works of Farber, Pajitnov-Sikorov, and others. So what happens if you don't just look at one parameter families, but you just you could look at all possible complex cohomology classes and ask how these cohomology groups jump. And it will again have this similar behavior. There will be some hyperplanes where the cohomology groups jump. But generically, you're going to get one answer. Okay, so this is one approach to define this space of states. Now, this is not something you can do if you consider the space of connections. Space of connections something infinite dimensional. Formally, you could try to define this twisted Rham complex, but you will not get the right answer. And even if you get the right answer, yeah, basically it's going to be difficult to compute, and yeah, so this is not the right approach, at least for me. Okay, so let me mention another approach, which is also not something I'm going to consider, but another way to define this space of states. And this again described in the same paper written. So let's say this one form, alpha, is actually differential of a circle-valued Morse function. So of course, then alpha is this integral cohomology class. Okay, so if you have a circle-valued Morse function, you can lift it to the cover of Y. So X is Y. So you can lift the circle-valued Morse function to a cover of Y to get a Morse function on the cover. And in this case, you can compute what's called Novikov cohomology. So the setup is similar to the usual Morse complex. So you look at a vector space generated by critical points of the Morse function on the cover. But then there's going to be an action of duct transformations. So Y duct transformations for this Z cover. So this complex or this vector space will actually be a module over Laurent polynomials, and then you can complete with respect to T. So that's the Novikov complex, and then there's a differential, just like in Morse homology, counting gradient flow lines between two critical points. Okay, and then the original theorem of Novikov is that this Novikov homology or Novikov cohomology is isomorphic to exactly this generic homology, except Novikov homology is defined over the Novikov field. So you have to tensor coefficients from C to formal Laurent series. Okay. So I'm stating it here because I want to give, and I'll state analogous theorems that will have similar shapes. So yeah, this is a nice motivating example. So again, I can't apply this in a case I'm interested in, the space of connections. So again, I want to consider Y being the space of connections. One problem is that this isn't something infinite dimensional. So it's non-compact. The other problem is that you actually have to do a covariant Novikov homology. So there's a lot of analytical difficulties in making sense of that. So again, this is not the approach I'm going to take. So let's look at some other versions of this space of states. Now, there's something special in the example that I'm talking about, namely that this space, this moduli space of connections on the three manifold, this is actually an infinite dimensional complex manifold, so even Kähler manifold. And the potential is given by a holomorphic function. So the Chern-Simons functional, the complex Chern-Simons functional, is actually a holomorphic function, maybe modulo integers. So let me consider this situation that you have a complex manifold and you have some holomorphic function, which is not necessarily Morse. But 0 is for simplicity, let's say 0 is the only critical value of this function. Okay, so something to consider is the sheaf of vanishing cycles, or the cohomology of the sheaf of vanishing cycles. So let me just briefly recall what this is. So let's say you look at the critical locus of the function. So zeros of df. So it's some analytic subspace of y. And so on this subspace, there is a natural perverse sheaf, which is the sheaf of vanishing cycles of f. Now, in general, it's a little bit difficult to understand, but if the critical locus is actually smooth, so you're in the Morse-Bott case, then this perverse sheaf is actually just a shift of the constant sheaf. So in this case, the cohomology of the sheaf of vanishing cycles just reduces to the usual cohomology of the critical locus in the Morse-Bott case. Okay. So let's again look at the twisted Rham complex. And again, in this twisted Rham complex, I'm going to introduce a parameter. So I want to talk about this sort of generically twisted Rham complex, generically twisted Rham cohomology. So I'm going to introduce a parameter which is usually called h bar in this setting. So h bar is the inverse of tau that I was talking about before. Okay, so you can look at this twisted Rham complex, and I'm considering this twisted Rham complex over the field of formal Laurent series. So what I'm changing is I'm multiplying the Rham differential by h bar and keeping the twist the same. Okay, so in this case, again, there is a description of this cohomology of the twisted Rham complex. So there's a theorem due to Saba and Saito answering a question of, or a conjecture of Kontsevich, that this cohomology of the twisted Rham complex, so it's again something defined over formal Laurent series, is actually isomorphic to the cohomology of the sheaf of vanishing cycles. Again, the sheaf of vanishing cycles is actually something defined over C or even over the rational numbers. So I need to base change at the right-hand side from complex numbers to formal Laurent series. And in fact, the statement is a bit stronger in this case. So the sheaf of vanishing cycles has a monodromy operator. So there's a certain automorphism of the sheaf of vanishing cycles given by monodromy of vanishing cycles. And using this automorphism, you can introduce a connection on the right-hand side. You can introduce a connection on this formal disk whose monodromy is given by T. And so Saba and Saito identified this connection on the right-hand side with the natural connection on the left-hand side. So there's another connection on the left-hand side defined purely in terms of the potential. I won't get the signs right, but it's something like h bar squared dd h bar minus f. So there's a question about the assumption that I made about 0 being the only critical value. So it was important to state the theorem. In a second, I'll talk about slight generalization of the sheaf vanishing cycles where this assumption will not be relevant, that 0 is the only critical value. So in general, you'll just sum over possible critical values of the potential. Okay. Okay, so now I want to go back to Dan's question, which is how much supersymmetry this supersymmetric quantum mechanics has, and whether we can actually use that to actually get a better handle on this on the supersymmetric quantum mechanics. Okay, so originally I was talking about the case where Y was a Riemannian manifold and alpha was some closed one form, maybe differential or potential. But in this case, the potential is the real part of some holomorphic function on some Kähler manifold. So in this case, supersymmetry gets enhanced. So originally, supersymmetric quantum mechanics had n equals 2 supersymmetry. If you assume that you have a Kähler manifold and the potential is a real part of a holomorphic function, you're going to get n equals 4 supersymmetry. Now, the reason I'm pointing this out is that once you're in a supersymmetric setting, there's something nice you can do. You can talk about supersymmetric twisting. So you can actually get a TQFT out of these supersymmetric theories. And I am talking about supersymmetric twisted quantum mechanics. But because I have more supersymmetry, I have n equals 4 supersymmetry, there will be more twists. So there's actually going to be a family of TQFTs parameterized by possible topological twists. And the original supersymmetric quantum mechanics, so the twisted supersymmetric quantum mechanics is going to be just one value of this family of TQFTs. So there's some nice family of TQFTs, and let me just call this parameter h bar. So h bar is in general on CP1, but I'm just going to consider it on C. So h bar is not infinite. And at the special value of h bar, when h bar is 0, the corresponding space of states in the twisted supersymmetric quantum mechanics has a very easy description. It's just given in terms of the critical locus. So it's the cohomology of the sheaf of functions on the critical locus. So O is the sheaf of functions of holomorphic functions. So this is a one-dimensional analog of the usual B model in 2 dimensions. And the usual supersymmetric quantum mechanics is a one-dimensional analog of the A model in 2 dimensions. And now you have a family of these two QFTs parameterized by CP1. And you can ask what happens when you deform from H bar is equal to 0 to H bar is equal to 1. And one way to describe it is in terms of what is called Batalin Vilkovisky quantization. So the critical locus of a function has a natural Poisson bracket of cohomological degree 1. So in physics, it's usually called the anti-bracket. And then once you have an anti-bracket, you can talk about its quantization. So you can ask about lifting this anti-bracket to a BV Laplacian. And this is the kind of BV quantization I'm talking about. Okay, so the upshot is that due to the fact that you had this family in this case, your answer for H bar is equal to something generic is going to be deformation quantization of the critical locus. So that's kind of the explanation why there's something nice happening in this case when your manifold is scalar and your potential is a real part of a holomorphic function. So this is described in the paper with Brian Williams. And let me remark that this is completely analogous. So in fact, this setup was based on paper Kapustin, where he described a similar phenomenon in 2 dimensions. So when you look at the usual supersymmetric sigma model into a hyperkähler target, then its supersymmetry is enhanced. So in the case of a Kähler target, you would expect 2,2 supersymmetry, but in the case of a hyperkähler target, you're going to get 4,4 supersymmetry. So in this case, again, there's going to be a family of topological twists of this supersymmetric sigma model, which are going to interpolate between the usual A and B models of this hyperkähler manifold. And using this picture, Kapustin explained why in this hyperkähler setting, the A model or the Fukaya category has something to do with deformation quantization of the corresponding holomorphic simplicity manifold. Okay. But for me, yeah.
Sorry, are you assuming the critical locus is smooth in this slide?
Good question. So no, I'm not assuming the critical locus is smooth. Here, yeah, there's something simpler happening when the critical locus is smooth. But no, it's just some general critical locus. So to talk about Batalin-Vilkovisky quantization more precisely, you actually have to talk about the derived critical locus, but maybe let me not quite get there. Okay, so I want to use this as a motivation to give some model of the spaces of states in some theories with extended supersymmetry, like 4-dimensional n plus 4 spring MLs. And again, in this setting, because I want to talk about things like deformation quantization, I'm only going to consider generic quantum parameters. So you can think that H bar is something generic, or H bar is something close to 0. So maybe working over formula Rham series in H bar. Okay. Okay, so this is the end of the kind of physical introduction to how to think about spaces of states in supersymmetric quantum mechanics. So now I want to switch gears and talk about a sort of mathematical approach to defining these spaces of states, which will then be used to talk about the space of states in n=4 spring-MLs. Okay, so are there any other questions?
So for Chern-Simons, you will need special values of h, yeah, integer level and so on.
No, actually the opposite. H bar. So
no, in the end, you will need to make a prediction about the integral over the space of compact, say, SU2 connections. So if you work with generic H, you complexify, that's fine. But then in the end, you will have to go to roots of unity.
Right. Yeah. So I'm not going to talk about roots of unity and things like that. I will only talk about this generic Q, so generic H bar and things like that.
I thought you were doing complex Chern-Simons, so you could analytically continue in K. Is that not right? Have I not understood?
Yeah. That's understandable. But in the end, if you're interested in the physical Chern-Simons, you'll need to derive the integral of the compact cycle from the integral over these symbols or whatever when you work for generic H bar.
Yeah, that's right. Yeah, but I'll not talk about that.
Mm-hmm.
All right. So let me talk about some math that's used to talk about these things like BB quantization of the critical locus. So the setup that often happens in this sort of physical approaches is that you start with some Kähler manifold, except it's infinite dimensional. So this Kähler manifold might even be not quite a manifold. It can be a manifold equipped with the group action. And then you have a closed holomorphic one form. And what you're interested in is the zero locus of this holomorphic one form, which happens to be finite dimensional in some sense. So I'll give one example in a second. But that's the setting. So even though the original manifold you're starting with, where you have the potential, is infinite dimensional, the zero locus is finite dimensional, except it might be sort of complicated. It might be singular. Okay. And I want to use this fact that it's actually something finite dimensional to make sense of this supersymmetric quantum mechanics and the corresponding cohomology. Okay, so the main example that I'm talking about, as I mentioned before, is the moduli space of connections for some complex Lie group. So again, think G is SL2C on some closed-oriented 3 manifold. And then alpha is the differential of the complex Chern-Simons functional. So then the zero locus of alpha just means critical points of the complex Chern-Simons functional, which are the same as flat connections. So now I'm just talking about the moduli space of flat connections on the 3 manifold M. And you can identify this moduli space of flat connections with monodromy representations. Namely, you look at homomorphisms from the fundamental group of 3 manifold into G and consider that up to conjugation. So because M is a closed-oriented 3 manifold, pi1 is some finitely generated group. So this is actually a very reasonable space. It's some subspace, some analytic subspace of some power of G modular group action. So this is what I want to point out, that I started with something infinite dimensional, which is the space of all connections, and ended up with something finite dimensional, except it's possibly singular. So that's the only problem to actually make sense of things. There's one thing that you might be worried about. You have to take a quotient by G, but I'm just going to work with stacks. So I'm just going to remember this extra G action. Okay. And so, all right, so you have this finite dimensional object. Can you remember the fact that it came as the critical locus of something? There is an extra structure that actually remembers the fact that some space is a critical locus of something. And this is the theory of D-critical structures that Joyce introduced. So here D stands for derived. But let me just say that X is not derived. X is some complex analytic space, maybe complex analytic stack. Okay, so in this theory, so that there's a notion of a D-critical structure that I'm not going to introduce. So if you have a complex analytic space with a D-critical structure, it's what's called a D-critical locus. And again, the main example is that you have a critical locus of some holomorphic function on some complex manifold. Okay, so in this setting, there's going to be one important bit, which is called orientation data. So this notion is due to Kontsevich and Sogelman. So this orientation data is that you have to choose a square root of a canonical bundle. So as I said, this space is singular, but the fact that it's a D-critical locus allows you to define a certain line bundle. And so taking square roots of this line bundle makes sense. Okay, so there's some virtual canonical bundle on this D-critical locus you can define, and orientation data is just choice of square root of this virtual canonical bundle. And then once you have a D-critical locus with an orientation data, Joyce and his collaborators constructed a certain natural perverse sheaf on this D-critical locus. So this perverse sheaf is modeled on the sheaf vanishing cycles. It's some gluing of the sheaf vanishing cycles. Okay, and once you have an oriented D-critical locus, you can take cohomology of the sheaf vanishing cycles. And that cohomology has a lot of interesting structure that's somewhat mysterious in the examples that I'm going to be talking about, which is it has a mixed Hodge structure, and from the sheaf vanishing cycles, it has a monodromy automorphism. So there's extra structure you wouldn't have expected if you just worked with ordinary supersymmetric quantum mechanics, where you just have Riemannian manifolds rather than Kähler manifolds. Okay, and let me just remark that this theory is a relative, so I used the word categorification of the theory of virtual fundamental classes. So if you're familiar with this theory, you can talk about virtual fundamental classes of certain moduli spaces, maybe moduli spaces of solutions of some PDE. In this case, let's say you have a PDE whose linearization is some real elliptic operator. You can talk about orientation data on this moduli space as orientation of the corresponding determinant line. So this is analogous as kind of complex version of the same. So there's a square root of some complex line bundle rather than an orientation of a real line bundle. Okay. And so this is the setting I want to consider. I want to consider this critical cohomology of the character stack of a 3-manifold. Okay, so the first thing to ask to even define everything, you have to have an orientation on the character stack. So you have to have an orientation data on a character stack. So it turns out that there's something much stronger than orientation data. So let me just recall that orientation data is a choice of a square root of this virtual canonical bundle. In fact, there's something stronger. There's a trivialization of the virtual canonical bundle. So there's a natural holomorphic volume form on the character stack. So this is some work that should appear soon on the archive with Florian and F. So if you have any unimodular algebraic group, so for instance, again, G's SLN-C, or any simple algebraic group, it's unimodular, and then this character stack of 3-manifold has a natural volume form. So the way this volume form is constructed is by constructing Reidemeister torsion. So Reidemeister torsion is something you can make sense of if you have a local system on the 3-manifold, you can take its Reidemeister torsion. So here I'm taking that joint local system. So you can take its Reidemeister torsion, and you can actually make sense of that in families. So that's what this work is doing. So this adjoint Reidemeister torsion defines for you a holomorphic volume form on the character stack. And just as an example, so this actually works not necessarily for 3-manifolds. You just need some finite stability complex. So for instance, you can consider the case of an oriented surface, in which case this character stack has a symplectic structure. So it has an idea about symplectic structure, maybe generically. And once you have a symplectic structure, you have a symplectic volume form. And so this is essentially observation of Witten that in this context, this adjoint Reidemeister torsion coincides with the symplectic volume form in 2 dimensions. In 3 dimensions, of course, you don't have symplectic structures, so you don't have symplectic volume form. Nevertheless, you still have this adjoint Reidemeister torsion. Okay, so once you have an orientation data, you can make sense of this critical cohomology of the character stack. And I want to talk about that. So this cohomology is closely related to what Abazid and Malescu considered. In the case of SL2C, they wanted to make sense of complex-variate version of instanton Floer homology. So if you think about instanton Floer homology, it's something that arises as the space of states in pure 4D n = 2 supergang mills. And so when you move from 4D n = 2 to 4D n = 4 supergang mills, you get complexification. Okay, so let me talk about this critical cohomology of the character stack. So I'm going to want to relate this to something very classical, which is the notion of a Skein module. So let's again say that M is some closely oriented 3-manifold, and G is some semi-simple group. Again, think about SLN-C. So then you can consider the Skein module of the 3-manifold. So the Skein module is going to be the space so it's going to be a vector space over Laurent series in H bar. It's going to be spanned by graphs embedded in the 3 manifold, and the edges, so some picture like this, and the edges will be labeled by representations of the group G. So more precisely, the edges are labeled by representations of the quantum group. But in this case, they're the same as just representations of the ordinary group. And then from the braid monodal structure or the ribbon structure on the category representations of the quantum group, you can get certain natural local relations on these graphs. So you look at the space of all graphs modulo some natural local relations. So let me talk about this very, very classical notion, which is the Kaufman bracket Skein module. So this is the case when the group is SL2. So in this case, you don't even need to talk about graphs. You can just talk about framed unoriented links modulus specific relations. So the relations are that if you see an unknot, then you can remove it at the expense of some factor. And then if you see a crossing, you can resolve it in 2 ways, and you get, again, some factors. So everything is phrased naturally in terms of this variable q, and q is the exponential of h bar in my notation. Okay, and so what I want to explain is this statement that we're proving with Sam Gunningham, that if you look at this critical cohomology of the character stack, so let me just try to read this this conjecture. Okay, so I'm looking at the critical cohomology of the character stack. Now, because I'm working with stacks, of course, you have to be careful. And being careful just means you need to be careful what you mean by cohomology on a stack. So I'm not going to say much about it, but there's a certain renormalized cohomology I need to consider. So let me just ignore this issue. And so this cohomology is going to be concentrated in non-positive degrees. So I'm going to take the top cohomology. Again, this is defined over complex numbers, and the claim is that the Skein module is actually isomorphic to this critical cohomology once you base change from complex numbers to Born Laurent series. Okay, so this looks quite unexpected. The left-hand side is something purely topological. You're counting links embedded in the 3 manifold. The right-hand side has something to do with the topology of the character stack. So this is, yeah, could be somewhat surprising. So let me explain where this conjecture comes from, and also outline some steps that we have already proven towards this conjecture. Okay, so the first goal is to actually relate this critical cohomology to deformation quantization. And the reason deformation quantization appears in this context is due to a theorem that we've proven with Sam, Gunningham, and David Jordan, which is as follows. So let's say, okay, you have this 3 manifold, and you consider a Haggard decomposition. So this is your 3 manifold, and it's split as a union of 2 handle bodies along some Haggard surface, sigma. So using this Haggard splitting, you can actually present the character stack in a very nice way. So the character stack in this case can be written as an intersection of 2 holomorphic Lagrangians in certain holomorphic symplectic manifold, modulo the group action G. So this holomorphic symplectic manifold is actually an open subset in G to the power 2G. So there's a natural Poisson structure, it has an open symplectic leaf, which is this S. And then this is what's associated to sigma, and the two handle bodies give rise to holomorphic Lagrangians in that symplectic manifold. And everything is G covariant, so actually you can take quotient by G at the end. So that's the representation of the character stack. All right, so the claim is that the Skein module is related to differential quantization. Namely, this symplectic manifold has a certain natural algebraic differential quantization. So actually, when I say homomorphic Lagrangians, everything is actually an algebraic variety. So all of these are algebraic varieties. Okay, so there's a certain deformation quantization of this symplectic manifold, and there are deformation quantizations of the Lagrangians, so that the Skein module can be written as a tensor product of these two differential quantizations. Okay, so that's the relationship between the Skein module and deformation quantization. Now, I wanted to relate Skein module and this critical cohomology. So to explain how this is related, I need to relate critical cohomology and deformation quantization. So let me do that.
Excuse me, one should be left module, the other one should be right module. What that means at the level of L1 and L2. You take tensor product over non-commutative algebra.
Exactly. So M1 and M, so yeah, in this setting, M1 and M2 are the corresponding modules. So M1 is a right module, M2 is a left module. But if you have a Lagrangian, you can talk about quantizing it to either left or right module. This A also has a certain anti-involution.
Okay.
So you can turn left into right modules and vice versa. Okay. So yeah, so let me explain the relationship between this critical cohomology and differential quantization. For this, let me just briefly recall certain works on differential quantization of holomorphic symplectic manifolds, which is the setting that I'll care about. So if you have a holomorphic symplectic manifold, there's a certain canonical differential quantization of that. It's denoted by W. So it's not quite a sheaf of algebras, what you would expect. It's actually a differential quantization algebroid, but it's enough to talk about modules. And then if you have a holomorphic Lagrangian in this holomorphic symplectic manifold, together with a spin structure. So in this case, the spin structure is a choice of a square root of the canonical bundle of the Lagrangian. There is a canonical differential quantization of this Lagrangian, so module over the differential quantization of the manifold. Yes. Okay, and then you can take this tensor product for two Lagrangians. So these are some sheaves on L1 and on L2. So the tensor product is going to be sheaf on the intersection. And one fact that's known is that this is actually a perverse sheaf on the intersection. Okay, so I'll put a remark here that this this category of holonomic modules is actually related to, on the one hand, what I call microlocal perverse sheaves, sort of topological category, and on the other hand, to the Rham category, which is slightly more analytic. Okay, so you can think of this as some kind of version of Fukaya category. Okay, but now if you look at this intersection of two Lagrangians, this intersection of two holomorphic Lagrangians is actually a D-critical locus. So you can interpret the intersection of two Lagrangians as, for instance, the critical locus of the symplectic action functional in the path space between the two Lagrangians. So that by this general yoga will endow it with decreased structure. And now if the Lagrangians have spin structures, so have square roots of the canonical bundle, then this intersection will have an orientation data. Okay. So this is good. This says that actually in the setting, I can talk about this sheaf, the perverse sheaf that Joyce has constructed with collaborators. And so the theorem that we prove with Sam Gunningham is that you can identify the perverse sheaf that comes from deformation quantization and the sort of globalization of the sheaf of vanishing cycles. Okay. So the theorem is actually a bit stronger, just like in the Sabasaita statement. It's not just an isomorphism of perverse sheaves. The right-hand side has a natural connection, and there's an interpretation of this connection on the left-hand side, just like for the twisted around complex. Okay, so this is essentially what's needed for the proof of this conjecture. There's one, so there's a few loose ends. There's a fact that I'm actually here talking about algebraic deformation quantizations, but on the next slide, I'm talking about analytic deformation quantizations. There's a certain Gaga type theorem that needs to be proven. And second, just making sure the orientation data matches. Okay, but the second one should be pretty minor. Okay, so this is most of what I wanted to say. So let me just end with some questions. Okay, so let me just write the conjecture again. So again, the conjecture is that there's something purely topological, which is you count these links or graphs embedded in manifold, modulo some relations. And the claim is that that's actually isomorphic to some topological thing, which is cohomology of the character stack with coefficients in this perverse sheaf. Now, the right-hand side carries a modularity action. So there's a natural connection on the right-hand side. So this connection should go to something interesting on the left-hand side. You can, if you think about the corresponding physical setup, it's actually related to Langland's. It's a kind of weak shadow of Langland's duality of n equals 4 Spring Mills. But nevertheless, it should be seen as a certain natural connection on the Skein module. And then the other question, which is pretty natural, is what is the mixed Koch structure on the right-hand side in terms, again, in topological terms. So this should be related. There are some computations that show that it might be related to evaluating the skeins at roots of unity, but there's no precise conjecture at the moment. So I'm going to stop here. Thanks.
Thank you, Pavel. Thank you for a great talk. Questions, please raise your hand or just jump in. Charlie from?
Yeah, so you can form the Hochschild cohomology of that bimodule built from the Heegard splitting over the Skein algebra of the surface. Is that going to be isomorphic to the full cohomology of your sheaf over your object?
Yeah, essentially. So there's so sort of derived version of this is that indeed you take Hochschild homology or just derived tensor product, and then you have to take group homology of that. So G naturally acts on everything. You have to take group homology, and that's going to be isomorphic to that critical homology.
I see. Cool. Thanks.
Other questions?
Yeah, I have kind of question, maybe remark, I don't know. But let's start with the question. So you can think of Chern-Simons functional originally as a holomorphic function on some, let's say, universal cover, maybe of some space of maybe stack, maybe space of frame connection, it depends. And then you just treat it as a holomorphic function on infinite dimensional manifold and get another sheaf of vanishing cycles, yeah. And essentially do the same thing to consider cohomology with coefficient in that sheaf, something like treating the whole story as a kind of Landau-Ginzburg model on the infinite. Okay, and there are some evidences that that a cohomology with coefficient in the sheaf of vanishing cycle, they have mixed Hodge structure, and the weight structure is non-trivial. So in terms of Chern-Simons, this weight non-triviality is reflected by the fact that expansions in the of the Chern-Simons had connections with larger stabilizer can see expansions, perturbative expansion in the connection with smaller stabilizer, something like that. How you can see this when you already work in the finite dimensional setting with the Skein modules? Is there any science of I mean,
yeah, that is exactly this second question. I have no idea. Yeah, so on the right hand side there is a natural mixed Hodge structure, and it should go to something on the left hand side, and there isn't a natural reason to expect a mixed Hodge structure on the left hand side, because again it's just given by counting some links. So I don't know the meaning of that.
Yeah, I'm not sure even that on the right hand side what I'm saying is the same as what is written on that slide. So it's kind of, because you, yeah, I think it's maybe a bit more complicated. And another thing, indeed, there is this industry of like people looking for the resurgent properties of the Chern-Simons perturbative expansion. You have this Laurent polynomials in H bar. So any kind of predictions about analytic?
Yeah, I would love to know anything related to that. I don't know anything about resurgence, but yeah, indeed, based on your works, I would guess that it could be something like that. Could be an answer to these questions, but I don't know exactly.
Okay, yeah, thank you.
Andy, do you have a question?
Yeah. I just wanted to ask, so in your first open question here, you mentioned an H-bar connection, but I didn't understand H-bar connection over what space? Yeah,
so it's a so this is just a vector space that depends on H-bar, and it's just mean a derivative, something that allows you to differentiate with respect to H-bar naturally.
Oh, a connection in the H-bar direction.
Yeah,
okay.
Yeah.
Thank you.
Pavel, from this conjecture, does the finite dimensionality of the Skein module follow?
It's a funny question. Almost. Okay, so one problem is that, okay, so if you have a perverse sheaf and you consider its homology, and the sheaf is algebraically constructible, so then the push forward will still be constructible sheaf. In that case, it's going to be fine dimensional. This setting is a little bit funny. You have an analytic per sheaf, which is constructible in analytic respect to possibly analytic certification. So I would say that it doesn't immediately follow, but possibly some experts would be able to say.
I think you have to be careful about coefficients to get it be finitely generated.
Okay, thanks. So Pavel, there's a question in the chat.
Yeah. So the question, the critical locus of Lagrangian in the derived critical locus. So in general, so if F is Morse bot, so the critical locus is smooth. In this case, it is true that the critical locus will be Lagrangian. So in general, it's not true. So you could have, like, for instance, if DF forms a regular sequence, then the critical locus will be just isomorphic to the derived critical locus. So it can be possibly Lagrangian. Yeah, so the sheaf vanishing cycles is related to just differential quantization of the derived critical locus. It's unrelated to this kind of Lagrangian structure.
Okay. Any other questions? Well, then let me remind you that in 2 weeks, we'll have our final WHCGP, will be Sam Raskin. And let's thank Pavel again for a beautiful talk. Very good. Pavel, I'm very ignorant about these orientations being a square root of a complex line bundle. You said at some point, you said two things that were interesting. One, you said there's